Hi there. Hi, everyone. Good afternoon. Welcome to GSA Footfall Analysis. For this afternoon, what we're going to do is we're going to give it just a few more minutes for a few more people to join. We are expecting a few hundred today, and so we'll get started in just a couple of minutes. Just give them give people a few more minutes to arrive, and I will make introductions. I'll start by introducing myself. I'm Andrew Eckert. I'm the Business Development Manager for the GSA software here at Oasys. And today our presentation is going to be put to you by Peter Debney, Chartered Engineer and a Fellow iStruct. Okay then, without further waiting then, Peter will launch into today's webinar on footfall analysis. Peter, I'm handing over to you, but before I do, if anybody has any questions during today's webinar, please pop them into the chat. And then when we reach the end of today's presentation, I'll read through the questions and Peter or perhaps one of our other experts will be able to answer your questions as we go through. If we don't have time to answer them all, we will try and get back to you with those answers in the next day or two. Right, Peter, over to you.
Okay, thank you very much, Andrew. Yeah, so footfall vibrations, Dave. So the footfall vibration is essentially a vibration caused by footfalls or people walking, and the analysis we're looking at here is essentially how lively a structure will be when people walk on it, and what we mean by liveliness for that matter. So dangers and problems from structural vibration is problems we've known about in the industry for a long time. Earthquake damage, for example, wind-induced torsional failure of the Tacoma Narrows Bridge. You know, these are all ultimate limit state problems which can lead to the collapse of the structure. But with footfall vibrations, this is something different. This is a serviceability limit state vibration, which is more about discomfort on the office or on the stairs or operational problems such as we get in laboratories and hospitals. So when people walk along, their feet impact the surface and this generates an impact force, and people tend to walk at a given pace, and as the frequencies of the impacts are reasonably regular, these can set up resonances with the natural frequencies of the structure, which then cause it to vibrate. But also you do get some floors which don't resonate because their natural frequencies are very high, and there we're looking at the momentary or transitory vibration problem which occurs on each step. Now, there have been a number of design guides over the years to assist with dealing with the footfall problem. One of the first was the American Institute of Steel Construction's Floor Vibrations for Human Activity, which was published way back in '97. Since then, we've had a number of further design guides. So we have the Concrete Center SCI P345, design guide for footfall-induced vibration of structures. Then the Steel Construction Institute, which has published a number of guides over the years, updated their latest one, which is the P354, so on the floors vibration, a new approach. And then the AIC updated their design guide 11 a couple of years ago, which is based on all the various research and indeed the other design guides which have come out over the years. Footfall analysis has also started being included in some design codes, and we look to see that in more detail over time, and also some manufacturers' recommendations. So there is no one way of addressing this, apart from the GSA, of course. Now, some of the guides do have simple methods to estimate the footfall response. Now, in the simple methods, yeah, you take a standard floor, which is closest to your actual structure, calculate the first two natural frequencies. Then from there, you calculate the resulting velocities, accelerations, and response factors. Now, these do have a number of assumptions built into them, and it is difficult to make them match up with the majority of real structures. Also, of course, they have been shown by a number of sources to be quite unconservative and inaccurate in their results. But on the plus side, the formula there, 18 over the square root of the deflection, is actually quite reasonable at predicting, at least approximately, the natural frequency of a floor. So yeah, if you can get the deflection from your model, that should give you a good indication, not totally, but a good indication of what the natural frequency should be. Now, all the modern design guides do recommend that engineers use the finite element analysis approach. So this FE approach requires analysis of a subframe, so in the case of a floor, or indeed the entire structure in case of a stair or a bridge, so the entire structure, the entire staircase. And it's a two-step process. First of all, you need to analyze to get your vibration modes with their corresponding frequencies up to a certain cutoff point. Now, what that cutoff point is, it really depends on the design guides and the respective maximum walking frequency you're looking at, and also sometimes the fundamental frequency of the structure in question. Now, when the structure vibrates, it doesn't do with just one mode, which is the vibration shape or the frequency, but with several modes simultaneously, even though the software will supply you with each mode as a separate result. Now, these modes actually interact to produce some quite complex movements. And as you can see from the video on the bottom right, that is the three beam modes acting simultaneously, in this case, with I did a time history analysis in GSA to extract those. Now, if you're looking at floor vibrations, these are considerably more complex than single beams, which again, where the FE analysis comes in. Now, once you have the vibration modes, you then need to do a subsequent analysis to calculate the velocities, accelerations, and then response values. Well, I'll say you. And speaking, let GSA do it for you. Now, these values you need to calculate. The floor might be the peak values, or the root mean squared, or the root mean cubed accelerations, and these might be expressed in meters per second squared or %g, depending on the design code. And similarly, you might need to calculate the velocities, which might be in terms of meters per second or MIPS. And as I say, different design guides require different outputs in different situations. Now, when we're looking at people comfort, I think acceleration is the aspect we're most interested in, and it's their perception of vibration and whether this is a concern or not. And this depends on what people are doing at the time and their orientation. Now, people who are standing up, they are least sensitive, or people who are standing up and walking around may be least sensitive to the vibrations. People are most sensitive when they're lying down. You'll also note from the ISO base curve, the limit of human perception on the right hand side, that we are most sensitive in the frequency range between 4 and 8 Hertz. And these are apparently the frequencies which our internal organs resonate, which, yeah, you can understand that is going to make things uncomfortable or at least sensitive. Now, the downside is this is the range that most floors also vibrate at. Now, the AISC guide says you can just conservatively take 0.5% G for office floors, whereas other design guides recommend using a weighting curve to adjust the frequencies depending on how sensitive we are to them. And you see on the left, there's the weighting curve WG, which you'll note is sort of the mirror image of the ISO baseline curve. Now, GSA does include the WG curve and indeed other weighting curves, so you do have the option to get a little more assistance for frequencies over 8 Hertz. Under 8 Hertz, for a building, you shouldn't be getting those frequencies, but for a bridge, you might do. But anyway, generally, if you've got a footfall problem, you want to try and keep the frequencies high. Now, the relationship between the accelerations and the different frequencies and the limit of our perception give us the response, or our value, which is essentially an acceleration, or an acceleration in relation to the baseline acceleration curve. So the response of the structure to footfall is not just dependent on the frequency of the floor, but also the mass, or to be more accurate, the modal mass of the structure. So keep it simple, the modal mass is essentially the mass of the structure which is moving in any given vibration mode. So for example, you could have a long span floor which will have a low natural frequency, but it also has quite a high modal mass to resist the footfall force. So F equals ma, familiar formula, which you can rearrange, say A acceleration equals force over mass. Higher the mass, lower the acceleration. Similarly, a short span can have a high natural frequency, but as it has a low modal mass, it can experience high accelerations. In other words, a high frequency floor can have a high response, but again, not necessarily. You do actually need to run the various calculations for each situation. Now, I mentioned resonance just now. So what is that? Now, resonance is when the vibrations build up over time. And we take this example, we've got a floor which vibrates at a particular frequency. Now, if that frequency is the same as the walking speeds, then each footstep will push the floor more and more, which increases its amplitude and acceleration. What's more likely, though, is the footsteps may interact and resonate with every other cycle of the floor, because we exclude those very low frequencies from our design and prevent them from occurring. So if we're then interacting with the second harmonic, the footstep lands every other time that the floor bounces. Or of course, the third harmonic, or indeed the fourth harmonic. Now, there is a fallacy I've heard that says you need to have regular bays to build up resonance. Now, this is not the case. Because vibrations over multiple bays actually tend to have a large modal mass, which in turn lowers the response. The main problem is actually isolated bays, which do not interact with other parts of the structure. And these do tend to have quite a high response value, as they have a low modal mass. What can be important is the physical width of the mode, thus how many footsteps can fall in any given location. Now, if this resonance was unchecked, like the induced vibrations of Tacoma Narrow Bridge, it would eventually destroy the structure. Thankfully, structures do have imperfections in, and these imperfections absorb the vibration energy, and this is the effect we call damping. And you might also hear the term critical damping in vibration engineering. This is the figure of, or the level of damping where the structure will return to its original position in the minimum time after dynamic movement. More damping will slow return to starting points, and less damping means the structure can overshoot. So, as I mentioned, with no damping, you could have huge resonant vibrations where the natural frequencies of the structure coincide with the forcing frequencies or the walking speeds. Then you could get large applications of the structural movements, but how much depends on the damping. Now, the damping of a real structure ranges from about 0.3% to about 4.5% of the critical damping, which depends on the construction and the fit out. Now, resonance occurs with not just the fundamental frequency, but also the harmonics as well. And so here we can see huge application occurring when the forcing or walking frequency is the same as the structure, which is again why we normally ensure the fundamental frequency of the structure is higher than that maximum walking speed. So if we exclude that first harmonic, we can look at the second harmonic and beyond. So you'll note that we've got resonance occurring with the second, third, fourth harmonic, but also the fifth and sixth and so on, to an increasing diminishing amount. Now, we don't normally calculate beyond the fourth harmonic. We do for staircases, we only calculate the first two harmonics, because beyond that stage, It's people walk at a reasonably constant pace, but not sufficiently constant to have much influence on the high harmonics. Now, as well as the resonant responses, you can get transient or impulse, which is responses on high frequency structures where the vibrations die off before the next footfall lands. Thus, in this case, it's the first peak acceleration that's calculated, and here the damping has very little effect on the results. Now, to find the accelerations, we also need to calculate the force that each step generates. Now, not all the weight of the walk is translated into a force on the floor, and the design guides have recommended various dynamic coefficients or load factors, which correlate the weight of the person walking to the various harmonics and so on. Now, GSA does include these as standard already, but of course you can also add your own, which you may need to for certain cases. So we have the dynamic load factor table for these user-defined values, and that's a bit small. So zoom in a bit, and you'll see that we actually specify the harmonics, or specify the forcing factors, load factors for just the first range of frequencies, and we know that we don't need to specify the higher harmonics because the second harmonic is twice the frequency of the first, and so on. Now, you don't need to add these, but normally, but if you do, then they will appear automatically in your footfall analysis dialog, and any DLFs you've added will appear at the bottom of the list. Now, before we can analyze a model, we have to build it. So first thing to note, we will for steelwork structure, we will need to model both the steel beams and the floor slab, and we need to have a reasonable mesh density, which has to be sufficiently high to get accurate results. You're looking at 8 to 10 nodes in any principal span. Minor spans, you can get away with less, but major beams, 8 to 10 nodes. You can also note that strains are very small under footfall vibration. So this means that the shear in bolted, friction in the bolted connections is not normally overcome by the range of movements. So the footfall vibration would normally model all shear connections as being continuous or moment connections. We also need to make sure we offset beams and slabs to generate composite action, even if the beams themselves are not designed as composite in the ultimate limit state. The friction between a steel beam and a precast concrete plank, for example, is still pretty high as far as the vibration is concerned. Now, the American Guide Steel Designs Manual is slightly different. So the Concrete Center and the Steel Construction Institute's guides will say offset the beams and floor shells to automatically generate the composite properties. AISC Guide recommends you explicitly determine the composite section for each beam. Now, this does have the advantage that it gives you much greater control over the stiffnesses, and you can likewise increase the stiffnesses of edge beams and so on, and you don't have to worry about the neutral axis position. In principle, the neutral axis, all the beams should be at the neutral axis of the composite section, but to be honest, with multiple beam depths varies over the floor. But with the AISC approach, you can set the neutral axis depth explicitly for each section. Downside is you'll need to define the outline of every one of these sections, which is a little bit involved. Also, do watch out for self-weight or mass calculations. You can see there the floor slab has been converted into equivalent steel section, and there is a big risk of double counting the self weight if you're not careful. Now, it is also good to include the columns rather than just support points, and because these add stiffness to the floor. Now, how long these columns need to be is a matter of some debate. You can model them full height to the next floor and fix the ends, or you can go half height and pin the ends. But what you do not need to do in general is to model multiple floors, unless of course you're going to definitely expect sharing of vibration between the floors. Now, it's not so much for transfer structures because they normally carrying a huge weight, but yeah, there may be structures which do sort of hang off another and so on. Now, as far as partitions and cladding is concerned, you can include these wall lines as spring stiffnesses, or you can explicitly include them as shell or plates, or plane stress elements, I should say, or you can just pin them in position. Now, each design guide will have its own recommendations on the best approach if you take there. Now, you also need to have the loading. Now, unlike ultimate limit state modeling, in this instance, low weight is actually the worst case. So you should be including the minimum credible dead load and the recommended live load, which is normally 10% of the maximum. And GSA will then convert these loads into mass as part of the analysis. Of course, we know that mass resists accelerations, so actually low mass is more conservative. You'll get the lower the mass, the higher the response value. To model the slab, we have a couple of options. The first is to assume an isotropic behavior. We can model the slab, the full thickness, and then use a property wizard to set the properties based on the profile decking. And we can use a standard material for this. And then, you can either, if you're modeling the overall depth of the slab, you then need to reduce the weight, or if you model just the thin strip above the decking, which is a preferred approach, then we can add a little bit of weight on for the concrete, which is in the troughs. The second approach is to use an orthotropic material. So for a slab on profile metal decking is much stiffer in the span direction. Now, in GSA, we're modeling just the solid part of the slab above the decking, ensuring that it's offset correctly. And then we can give it an orthotropic material that increases one of the directions to account for the missing structure, plus additional mass. Now we can calculate the effective stiffness of the slab span direction by using the formula in the SCI design guide, which can give us the increased Young's modulus to compensate for the missing slab depth. So orthotropic materials rather than orthotropic elements. And if you're not quite sure what the I value of the profile deck aspect is, what I like to do is draw that as a perimeter section in GSA, and that then calculates the I value for me. At this point, we're going to look at how GSA works in action. So check this up here. So here is a model I prepared earlier. You might recognize this from it's a model I created quite a while ago, but it encapsulates a lot of the good parts of a vibration analysis. Now, here we have, in this case, I'm on the design layer, so I do have a number of steel beams with a single floor slab over the whole of it. Now, properties-wise, let's go into the section library. You see the various beams. We are taking standard sections, and we can use automatic offsets. Actually, in this case, I've offset the elements or members directly to the top flange. Likewise, we could offset the slab. In this case, we've offset it. It's been offset on the element itself. we also need to worry about mesh density. Now, the good thing about the good thing about GSA these days is that we don't need to. We can be quite flexible about the mesh density just by changing the mesh density on the slab itself. So, I mean, the default mesh density of 1 meter is actually looking pretty good. You can see the preview of what mesh is going to be created. If that was elements are too large, we could reduce the mesh density, and this will automatically change the meshing on the beams. Or maybe we have a larger mesh, and yeah, you can adjust this entirely to suit. But in this case, a 1 meter mesh is I think that looks about the right sort of thing. We then need to create the elements, and then I'll swap over onto the analysis layer, and there we can see the mesh structure. Now we do need to worry about the strengths. So in this case, I've modeled the columns as full height to the adjacent floors. So I'll just select those end nodes and fix them in position. And then for the cladding line, I mean, quite a small structure, what I'll do is I'll just go around, and now what I'll do is I'll select those north-south nodes, and I will give them a Z restraint and a Y direction restraint. And the other direction, give them a Z and an X direction restraint. And on this corner over here, maybe just a Z. It's too small to worry about. If it was a larger area, I could maybe give a rotated axis and so on, but I think that will suffice. I do know that you get this occasional pins in the corners, but that's entirely as we expect. Now for loading, so self-weight is calculated automatically, so gravity loading is unnecessary. What we do need is face loading, or on the 2D elements, which I've already set up. And it's a parametric load, so it's picking up the 2D element properties and automatically applying loads to those, as we can see here. So we can also look at materials. So steelwork, not so much, but concrete, yeah. When we're doing a footfall vibration, tend not to use the normal design Young's modulus, but use a higher value of 38,000, which might be changing. I think I've seen proposals in the Eurocode codes to maybe have this dynamic modulus of concrete based on the design Young's modulus. Here it is. Right, and this will need to be set in the 2D properties, and we can use the damped concrete value in our slab analysis. Steelwork, yeah, the Young's modulus is the same no matter how quickly we apply the loads. So I think I've got everything. So what we can do now is create, first of all, a modal analysis task. Though, for all the thumb, can be quite useful to quickly run a static analysis just to make sure everything is connected together and deflecting well. So, yeah, that looks not unreasonable. Delete those results and create a modal analysis task. Now, the question is, how many modes do we need? The exact number will depend on how big the structure is. This is quite a small structure. It won't need that many. What but we also need to know, is it a high frequency structure or a low one? So what I'm going to do, I'm just going to run a single mode just to begin with. I'm going to add in my dead and live load and take 10% of the live load, and you see the self weight has been calculated here automatically. I analyze that and see what we get. So the first mode, you can see we're getting frequency of 5.4 hertz, a very typical floor frequency. Now this is below 10, below 12. This is a low frequency floor, and so we need to go up to 15 hertz as a cutoff point to make sure we get good resonance analysis. Resonance will dominate in this structure. If this frequency was above 10 or 12, depending on the guide, this will be a high frequency structure, and we would need to have modes up to twice the fundamental frequency, either of the structure as a whole or the particular area of interest. So what I'm going to do, I'm going to delete those results, go into the task, edit it, and I'm going to say, let's say 20 modes, but we're not interested in modes above 15, so I'm going to have an upper cutoff and say ignore modes above 15 hertz. Now, so what will happen is that it might calculate those modes, but it won't save them. And run that. And so out of those 20 modes, you see actually the first 10 cover things. Okay, so what do we have? So obviously we can look at the results in the graphical view, and we can see the frequency in the corner, and we can look at the various modes, and they all look sensible. And of course, importantly, we haven't got the whole structure slewing sideways, which can happen if you've forgotten to restrain it properly. And these both look all right. We can also look at the numerical values. So go to the global results dynamic summary, and we can see we've got the modes from 5.5 hertz up to just shy of 15 hertz. Anyway, these modes all look good. So what we can now do is add in a second analysis task, which is a number response footfall. This uses the modal analysis as the base point, as we can see here. And note that if we had multiple modal analyses, which we can do, we could then have a choice of which modal analysis we choose. Excitation. Now, so the excitation is how are we exciting each of those? Now, are we just walking on one particular spot and measuring the response at that same spot, or are we measuring, or we walking on the spot and then measuring to see how that affects the rest of the structure? Now, self-excitation means excite the response node only, and this will generally give you the peak values, but won't give you sort of lateral as it effects. So one of the problems, for example, in, let's say, a hospital operating theatres, very stringent vibration requirements in an operating theatre, but also people tend to walk slowly in an operating theatre. It's general, but you might have people rushing past in the corridor just outside. Self-excitation would not pick up the effects of the corridor on the operating theatre, and for that we use the full excitation method. And we have three choices here. There is the fast option to give you a reasonable idea. There is the rigorous option, which does the whole thing. And in a more realistic model, or more realistic sized model, this can take several minutes. And there's also the full excitation rigorous, but excluding the response node, which means this will measure the response everywhere apart from the node or the point where the person is walking. Now, this doesn't make too much difference of floor structures and can be sensitive to mesh density, but on something like a staircase, where you might just have a single node on each tread, this option comes in very useful, because then it avoids that peak response on the tread which is being walked on, and just measures the response of the rest of the structure. In this instance, full rigorous is fine. We can also choose to have a cut down list of response and excitation nodes. In this instance, not a problem, but let's say we had handrail in the model for seconds. We're not interested in people walking on top of the handrail, and so on. So there are things we can exclude. Number of footfalls. How many footfalls do we need? How many footfalls will we get in a given mode? This will be the length of mode divided by an average floor, a step length, which is about 0.7 meter. So in this case, actually, let's just jump back and say, okay, let's go mode 1, and we've got a mode here. And how long is that mode? I can pick 10 nodes and ask the select properties, and you can see that is 17 meters long. So 75%, I'll call it 25. So footfall, plug station, whole floor, maybe 25 footsteps. Note this only affects resonance, not transient results. We have the weight of the walker, direction responses, which is the weighting curve we want to use, and the excitation method, which, yeah, use a concrete sensor method to begin with. We do have various other floor and stair options. We also have the maximum minimum walking frequencies. GSA will default to the extreme values, but if you know how the space is going to be used, you can bring in these values. To begin with, I'll leave them as full. The damping, which can also have more advanced options. If you're a more experienced vibration engineer. And let's analyze that. And that has finished. So let us look at the results. Switch deflections off, doesn't make too much difference. And the contours. So nodal results. So we do get quite a lot of options of nodal results. So we might, let's go for the summary first of all. Here we have the overall maximum response factor, which we can break down into the transient response and the resonant response. And you can see, as we expected, the overall is mostly the resonance. That's almost entirely. We can also get to more detailed results, such as peak velocities, accelerations, and so on, and also which is the critical frequency which actually caused that footfall. Similarly, we have the transient accelerations and so on. Now, we have these nodal values because this is where they're actually being calculated. What we like to do rather is actually smear these results onto the elements they're attached to, and then we get a much nicer full contour, which is, I don't know about you, but I find this much easier to read. We can also get the results directly from here. So if I just open up the summary of the summary, we can see that the maximum response is 8.6 on node 239, and transient response 4 on node 354. Different location. This is quite normal. On the other hand, if we want, we can get results in much more detail. Either the resonant results, so we can see the various. see. Yeah, we can see the results on some of the nodes, and likewise the transient nodes. There are various results in there to drill down and see exactly what's going on in detail. We can drill down even further. Actually, not that one. Let me just pull up the summary of the summary. Node 239. This is where the location we get the maximum footfall response. Where is that in the structure? Maybe one of these two red areas. I'll just find. Was it 239? That spot right there. Not unexpected. And well, what's happening at that spot? So let's go and look and draw up some chart views of the footfall analysis for that particular node. And so what we can do is I can look at the resonant analyses and the transient analysis for that location. And let's say speed, let's say 2.2, that's the worst value. And we get a number of graphs out. So first of all, the transient response. This is the momentary vibration, not governed in this case, but could be. And we can see we get the results for which modes drive the vibration at that location. So if you know you have got a high response, you might want to adjust the structure to not resonate so much at that location. And to do that, you need to know which modes are influencing that. In this case, mode 2 and mode 10 are most dominant. We can see the vibration acceleration over time and the velocity over time. The transient response versus walking frequency, and you'll note that it always increases with transient response, always increases with the walking frequency, walking speed. Reduce the top speed or walking frequency, you will reduce the transient response. Resonant analysis, different set of modes. Mode 2 again, but mode 10 has very little influence on the resonant analysis. So if you did want to address this particular vibration, mode 2 would be the one we might need to suppress. We have the dynamic load factors. We used the standard ones from the Congress to guide, and see if those are there already. And then we get the resonant frequencies, accelerations against forcing frequency, which is almost as useful as the next graph, which I think is my favorite. Let me just enlarge that a bit. So this is the response factor versus the walking frequency. And we see we are getting quite a complex result. And we are getting, let me put the cursor tooltips, call this at nearest points. So we are getting the peak value at a walking frequency of just over 2 Hertz, and the lower peak at 1.6 at 1.56 Hertz. Note that this is a walking frequency for 1 to 2.5 Hertz. If let's say we're working in the operating theatre, maximum walking speed, and the guy says 1.8 Hertz, we would have a cutoff at this point, and the response value was saying drop from 0.9 down to 0.6. That is quite low. That's the results. Yes. Now then, what else? How we do for time? Not too. We're running. Let me just quickly show you another model. Yeah. So. Yeah, I mean that was a very simple model, but here is a more complex model. And let me switch over and In this instance, yeah, we needed just shy of 100 modes to analyze this structure, and these modes will then go from very simple up to quite detailed and spread out. If we now look at the footfall results here, we can see that, yeah, in general, the floor is mostly good. One D elements. It's mostly good, but there are some definite peaks. And there is a peak down in this corner over here, which is a reasonably isolated bay. So we're getting a high response just in that area, but also we're getting a very high response next to these atriums. Now, let's say the target value was 8. There's lots of contours here. Let me adjust these contours. What I'm going to do is I'm going to specify. I'm going to say, let's say 8 in there, and then worry about what comes afterwards. So in this case, I've got blue and teal are okay, and then the yellows and oranges and reds are bad. So yeah, we have got a huge response next to this. This is an atrium. Is it a service duct? Staircase area opening. Anyway, unspotted edge. These are classic areas. Not only is an isolated mode, but also you've got a large free edge and no continuity. How we do this? Well, there are various ways of dealing with vibration problems. One is adding extra structure, maybe a supporting post, maybe a beam across, maybe increasing the weight of the slab, getting the slab to increase the mass. Actually, on that note, this increase in the mass. Let me come back to here. Yeah. Occasionally get support questions which say, I've increased the thickness of the slab, and the footfall response has got worse. This is a bit unintuitive. And you have to remember the effects of changing the structure and what that does on the vibration responses. So, for example, you increase the thickness of the slab. This increases the stiffness, and it also increases the mass. Now, increasing the mass will tend to lower the natural frequency and reduce the response, whereas increasing the stiffness tends to increase the frequency. So in many respects, increasing the thickness both makes it better and worse simultaneously. To what degree in each direction? Best you analyze it. But do note that changing the structure, changing the mass, changing the thicknesses, changing the beam sizes will move these peaks around left and right, up natural frequencies, but also vertically the response value. Now, if we look at this particular instance, so here we've got a footfall reduced result, and we've got resonance analysis, and we have 2 peaks. But note that these peaks is around about 1.7 hertz, around about 2.3 hertz. If we were to reduce the range of footsteps we're looking at from 1.8 to 2.2, suddenly we're taking quite a narrow slice through this graph, and we see the maximum response suddenly drops from 9 down to just under 4. Now, what can happen then is, if you're using the SCI guys, you increase, so let's say the mass, the thickness of the floor, This peak here does move down a bit, also moves left a bit. But the question is, where does that line then cross this 2.2 hertz? What can happen is, even though it moved down and left, this crossing point can then move up. So you effectively increase the response value by increasing the mass. If you move this peak right into this zone, well, it just pushes all the way up. So basic thing to note is that if we look at the walking speeds, say 1 to 2.5 hertz in the concrete center guides, and we look at the harmonics of those, they all overlap. The SCI guides much more focused, but there are gaps in between, which can be good because we can exclude these high values, but also the high values can hide, and we change the structure, they can move into view. As a general, whichever design guide you're using, ultimately, I would use the concrete center guide, get the full picture, understand exactly what's going on in the structure, and then after that, then refine it. Maybe use a different design guide, maybe change the range of walking frequencies as you see fit. Now, if you're looking at an existing structure, it's good to know what existing accelerations you could be expecting from Footfall. So at Arup, we do have a Footfall app, which is iPhone only at the moment. Uses the phone's accelerometers to measure the real structure's response. And I do know that Expedition has produced a similar app, this one for Android phones. And indeed, there may be others that I'm not aware of. So at this point, I'll say, yeah, if anyone has any questions, would like to learn more about thermal vibration or GSA, please do write them in the questions box. Or if you remember afterwards ever, you can just email us at the oasishour.com or my address, and we'll pick up that up later. So, Andrew, do we have any?
We do.
Any questions?
Look at what questions we have now. I'm going to read those out and see if you can't give us some answers. So, first question we have is, what versions of GSA can you do footfall analysis in?
Okay, so we have 4 versions of GSA with varying prices. GSA Analysis, GSA Building, GSA Bridge, and GSA Suite. GSA Analysis being the simplest, GSA Suite being absolutely everything. Footfall Analysis is included in GSA Building, GSA Bridge, and GSA Suite.
Right, okay, I'm going to pick on some more now. Right, so this one from Ibrahim Metwale. Can it do pushover analysis for RC structures? Can it do non-linear time history analysis for RC? And where might tutorials for those be found? Lastly, is it seismic design? So can you do performance-based seismic design? So all those questions come from the same person.
And dynamic, but not footfall. Okay. Seismic design. Yeah. So in GSA, whilst we don't have pushover analysis, we do have response, linear and non-linear time history analysis options. So yeah, so you can run all those are options. Yeah, and we have the seismic guides for all the major design codes. The instructions for those are included in the help file. Yeah. So yes, we do cover those.
Great. All right. Excellent. Now, it's a quick question. Possibly Neve's the best person to answer. We might answer this one. It's just someone asking for the PDF version of the presentation. I'm not sure that we do have one of those, but I will look into that and I will try and come back to you.
I've already answered those questions in the chat. So just looked out on our LinkedIn page for the updated link to the registration page, and we will update that with the video recording of this webinar.
Great. All right. Next one then for you, Peter. What natural frequency for the FEA elements will you set for a floor induced to rhythmic activities, i.e. gym or dance studio? As I believe it should be 8.4 Hertz. Can a 6 Hertz be used according to any guide?
Good question. I can't remember the detail offhand of the rhythmic activities guide. I would say do what's you either do what it says in the design guide, or if you have additional expertise in the area, justify why you don't. Because yeah, the design guides are good for standard cases, but not for all cases. So yeah, if the design guide says use 8 Hertz, then 8 Hertz is required. I mean, the first problem with rhythmic activities, you know, gym and that sort of thing, you get people running on the spot. That can be quite a high frequency of footsteps. Can that be as high as 6 Hertz? Maybe that's six footsteps per second. Those of you who've been to the gym recently might have an answer for that. But yeah, so the general rule is make sure the fundamental frequency of the structure is suitably above the resonant frequencies. Otherwise, yeah, you have to work a little bit hard to justify it to the checking authorities.
Okay, moving on. There's someone who's asked, what are those spring supports? But without knowing, that came in at 10 minutes to 3.
Oh, yeah.
Slide you were on at the time.
Yeah, the spring supports. Let me go and find that. I think I know which one that is. That'll be this one, I think. So this particular image, this was modeled using the AISC Steel Design Guide 11 recent edition, where they recommend using spring supports or spring properties on the nose there to where the wall lines are. So there are partition lines on those lines, and those springs represent the stiffness of those partitions. I presume that was the I think that's the only one with springs that I can remember. Yeah, I think so. Yeah.
Okay. Right. Our next question is, using the SCI P345. Is there a situation where you might consider just steady state or transient state analysis, or should you consider both in all instances, such as staircases and hospital wards, etc.?
Well, if I remember correctly, it says you would look at resonant analysis for when you're below 10 Hertz, and then transient analysis above 10 Hertz. But good thing about GSA is it automatically calculates both for you. That you can't switch them off. It does them both. They are free for you, and then you as an engineer can then make the decision which are appropriate to include. Yeah. Megas, we like to avoid black boxes. We like to give you everything, and then you can choose which is important. So yeah, that decision is entirely up to you.
Okay, so the good news there is that GSA does both of those analysis for you, and you can pick which answer you prefer. But both will be included in that package. The next question we have then for you, Peter, is somebody wants to know the definition of the number of footfall when we're assigning the parameter for the footfall analysis task. For example, number of footfall 20. Does that mean 20 steps on each node at every minute, or question mark?
Yeah. So the first of all, the 20 or whatever is based on the length of the mode. Let's pick. Let me go to 2D displacement. Oh, there we go. I'd forced the values, and let's say, oh, well, we can see that, you know, we've got this mode here, which is about that long, and I can pick that node, and see, well, how far apart are they? And we see that is 32 meters. And then I go, well, how many footsteps you get in 32 meters? I go, oh, 32 divided by 0.7, which gives me 45.6 steps. So we'll then say in the when we do the footfall analysis, I'll then put maybe 46 in there if that is the longest mode. Now we can, this is obviously in large modes and small modes, we can subdivide this, go vary with the different modes and say, well, that was mode 1, so mode 1 I do 46, but and then really drill down and fine tune each particular mode with each number of footsteps as appropriate. A lot of work. Now, what does this 46 or whatever or 20 actually mean? Now, strictly speaking, the person is walking along the floor, and so they won't excite each node directly. They excite each node in turn. But what we need to do in the analysis is actually excite each node with 46 steps, which on the face of it is a little conservative, but the design guys recognize this, and they then give it a formula which then reduces the results based on the effect of somebody actually walking. So it's an empirical approach to estimate the response and then reduce it to take into account that they're actually moving rather than essentially walking on the spot. Now this does fit in with their research because they use vibrating machinery to measure the responses of real structures to validate the responses, and obviously they don't walk around. So there's a certain amount of adjustment to the maths that goes in. Ideal case would be to actually model somebody walking, and then see what the response will be. Downside to that is you would need to model people walking at every possible frequency on every possible route over the floor, which would, well, that would be an astronomical number of calculations. It would be more accurate. Whether it would be worth the effort, that is a decision for you. But yeah, it's a shortcut to avoid the necessity to model every possible route, which would be a crazily large number.
Okay, well, we've got time to answer one more question, Peter, and
Okay.
then those of you who haven't had your questions answered, we have logged all of the questions that have come in, and you will receive email replies in the next day or two. But for now, the final question is, what would be effective ways of improving the vibrational response of an irregular floor plate in the interests of embodied carbon?
Oh, good question. Well, if it's existing or new builds, I mean, if it's new builds, try and make it more regular. That always improve that. Well, usually improves the vibration. Now, by carbon, quite a few customers have been using timber structures with a footfall analysis. Much lower carbon, also much lower stiffness, but the timber does have a good damping value. Yeah, so you can do that sort of thing. The other thing to look at is if your design has a particular problem, so you see, oh, this mode is causing the vibration. You think, well, how can I suppress that? So, I don't know, in this case, maybe a bigger beam across here, which ties those together. And a lot of this depends on whether the footfall response is actually governing the design or not. Sometimes alternate state is fine, and yeah, you check the footfall vibration, it's okay. Other times it's not good enough, and you might have to add in additional structure to make that work. If existing structure, yeah, you can add in additional structure. Alternatively, I did see one case where there was a particular hot spot in the existing structure, and the solution was stick a large plant pot there. Not only do people have to walk around it, there was also suddenly a large mass at the point of maximum excitation. Yeah, there is no one answer to a hypothetical design question.
Okay, well, I hope that answer will suffice. That was for Colin. So what we'll do now is I think Neva's made a note of any additional questions that we have. Peter, you can look forward to receiving those and answering them over the next couple of days by email. We'd like to thank all of you very much for attending today. And if you do want to get in touch with us, you can use the Oasys email address, which I think we had on screen a moment ago, and do get in contact with us. We can offer you a trial of the software, or alternatively, you can talk to either Peter or myself about the software at a later date. There's our phone numbers.
Yes.
So yes, in contact with us by email, and I can arrange for a trial of the software for those of you who don't already have it. Thanks again, everyone, for coming, and with that, we'll sign off. Thanks, everyone.
Thank you very much. Bye-bye now.